Okay, so let's start. I will prove fully the compactness result we have stated in class, which is the Rellich-Kondrachov theorem. Let me write it again here, and we will start from there. Let's see. Okay, so the Rellich-Kondrachov compactness theorem. Again, we already stated this in class and did some preparation steps, but for the sake of clarity, let me write everything here. So assume U in Rn is open, bounded with the C1 boundary. Okay, let 1 less than equals to P less than N, and surely P star is NP over N minus P. And 1 less than equals to Q strictly less than P star, not including P star. Then we have that W1P U is compactly embedded into LQ of U. Okay, that's the statement. All right, so in class, we have the separate preparation steps. So let me write out the proof in the various steps. The first thing is preparation steps. Although we are in a bounded domain U, but it started with a bounded domain U, but as we said, we can always use a compactness, extension theorem to extend everything to be sort of compactly supported in Rn with support in V. So everything is equal to 0 here outside and has compact support in V. So the first preparation step is about that we use the extension theorem to have that for a bounded sequence in W1P of U, we can assume that is in W1P of Rn, okay, with 2 points. The first thing is even extended to the whole space is still bounded by a constant for OM. Okay, and the second thing is that support of is in V. Okay, so it's compactly supported. That was the first step we did in class. The second step that is also very important is the fact that for H epsilon greater than 0, we consider the usual modifier eta, and then eta epsilon x is defined to be the rescaled of eta. Okay, and then we define again for h of we can smooth it out by using the usual convolution kernel, right? So we define for h in N that epsilon of x is nothing but eta epsilon convolute with of x, which can be written in two ways, either at the epsilon x minus y my dy, or at the epsilon of y u epsilon of x minus y dy. Either way, what we prove in class is that no, I'm sorry, there's a typo here. It should be there was an important inequality we proved in class is that okay, sorry, I should have write out one more thing, is that I also, without loss of generality, we can assume that support of u epsilon is in V. In fact, if it's not in V, you can just extend it, the set V to be bigger, to be W, and support is in W. We already talked about this. Then we have this inequality that u epsilon m minus u m in L1 of V is uniformly going to 0. Okay, where C is independent of m and epsilon. Okay, so this is a second inequality that is very important because it helps us to say that not only that u epsilon is close to um, but the closeness, the difference is small, dependent only on epsilon and not on m. Okay, so that's sort of the important point. Okay, and now we're gonna prove that you know, like using this preparation step, we're gonna prove the compactness result. Okay, yeah, so from this second point, there's the third point that we can see that now we can use let me modify this one to be clearer. Okay, and now we can by let's say star, the inequality star, and Holder inequality, we can in fact have the conversion of um epsilon to in LQ of V. Okay, so basically the idea is that we have already that the conversion in L1, and we have the boundedness in LQ star, and we're gonna use so we have the conversion in L1, we have the boundedness in LQ star, and sorry, P star. And if we take a point Q in the between, we can do as we said earlier about using Holder inequality to do the interpolation inequality, to interpolate that u epsilon m minus u m in L Q of V, right? It's gonna be, okay, let's write it down. This equals to integral on V. Okay, let's take it to power Q. Integral on V u epsilon minus um to the power Q dx. Now let's use Holder. This is less than equals to integral on V epsilon minus to the power Q. I'm gonna make it all the way to the power to the power 1, right? So I'm gonna take this to be this one. I will take it to the power let's see now what's the best way to write it down? um mm, let's see. Okay, what's the okay, maybe let me write this way so that it's less tedious. I'm gonna write as power s multiply with u epsilon minus um u epsilon m minus m to the power q minus s dx. Okay, and I'm gonna use Holder inequality here, and s is what is to be determined. This is less than equals integral v u epsilon m minus s to the power yeah, it's a bit tedious. P star over s to the s over p star multiply with integral on v u epsilon m minus m to the power q minus s to the conjugate Holder conjugate of this number p star over s, right? And then let's leave this power here, and then the remaining is to the power p star minus s over p star. Okay, so inside here it should be p star over p star. Sorry, it's just too complex. That's p star minus s over p star, and inside here should be p star over p star minus s. Okay, sorry, it's too much. So this is integral on v u epsilon m minus m to the power p star over s over to the power s over p star. This is bounded because we already have the Galiardo-Nirenberg-Sobolev inequality. This is bounded by u epsilon m w1p plus um w1p to some power, right? Which is bounded. What is important is that in the second term here, we want to make sure that this is the L1 because we have the inequality star over there. So this is in L1. And let's write this one down. This is integral on v u epsilon m minus m to the power, oh wow, p star over p star minus s times q minus s to the power p star minus s over p star. Okay, now we need to choose s. It's just a little bit of algebra and complications, but we choose s so that we have what? We have exactly that p star equals to p star minus s times q minus s, right? Because that's the s we need to choose so that the power is exactly 1. And if you believe me, it's just the algebra here. By doing it this way, then we arrived at the inequality that u epsilon m minus m in LQ of v is less than equals to constant times u epsilon m minus u m L1 of v, okay, to the power here and to the power theta, where exactly theta is this power, right? So theta is given by s, so you have 1 over q equals to theta plus 1 minus theta over p star. Okay, yeah, so that's the inequality. The key points that we have got from here is first that we have this inequality star, that um is close to epsilon is close to um by c times epsilon. And the second inequality we have now is that double star, which is important, is that epsilon minus in LQ of V is also less than or equal to c times epsilon to the power theta. Okay, that's the second inequality that is equally important, and it's independent of m. That's what is important, right? Okay, so we are done with the preparation steps. Wow, the step 1 is quite long. You can see here this is preparation steps. Now let's do step number 2. Is that we're now gonna use the fact that is a smooth up version of epsilon is a smooth up version of and we claim that for h epsilon greater than 0, for h epsilon greater than 0 fixed. Okay, now again, epsilon was a running variable, but now let's fix it and think of it as just a sequence of function in M. Then the claim is that we claim that u epsilon M is uniformly bounded. Okay, the boundedness is sort of clear and equicontinuous. Okay, we are using now sort of the equicontinuity, like what we did in class for the compactness embedding of C0 gamma. Okay, so now let's prove this claim. The first thing is it's not hard. It's quite clear that epsilon is bounded. All right, let's write it down. Just epsilon of x is equals to integral in Rn eta, wait, did I use eta? Yeah, eta epsilon of x minus y u my dy. Okay, and I'm just gonna squeeze the inequality in, right? So this is less than equals to eta epsilon in L infinity times with in L1, right? So integral, because has compact support, so y dy, which is L1. Eta epsilon it is a rescale version, so that's why it's bounded by constant over epsilon to c over epsilon to the n. This is bad as epsilon goes to 0, but for each of the fixed epsilon, this is bounded times with in L1, and by Holder inequality, this is less than c epsilon to the n, in LP as usual, which is less than equals to c over epsilon to the n. Okay, so it's bounded. Again, the boundedness is depending on epsilon, but we fix epsilon, so not a big deal. And similarly, let's bound the gradient, which is going in a similar fashion. The epsilon of x is equals to integral in Rn of d eta epsilon x minus y my dy, because I'm differentiating in x. So, and same game, this is less than equals to d eta epsilon in L infinity times in L1, which is less than equals to, I differentiate the eta function, then one of the epsilon pops out. So this c to the epsilon to the over epsilon to the power n plus 1, which is quite bad. But again, it's bounded for fixed epsilon times in LP, which is less than c over epsilon to the n plus 1. Okay, this is also bounded. Okay, so they're bounded, dependent on epsilon, but in this case, it's independent of m because we are considering the sequence with epsilon fixed and m is running. Okay. Then by Ascoli, yeah, now we can use Ascoli theorem. Then by the Ascoli theorem, we can see that there exists a convergent subsequence UMK converging to UL, let's call UMK epsilon, converging to U epsilon in uniformly. In V, right? Because V is compact. Okay. In particular, we also have that U epsilon MK is a Cauchy sequence, right? Because it's convergent. In C of V, okay, and it's a Cauchy sequence in C of V, meaning that in the L infinity norm, and also that I can see that I have furthermore that it's not just a Cauchy sequence in L infinity norm, but it's also a Cauchy sequence in LQ of V, right? Because you can use Holder inequality again, but this is an important point, right? There's a Cauchy sequence in LQ. All right, so now let's gonna use the final step, which is we're gonna use the step 3. We're gonna use the diagonal argument together with the Cauchy sequence and the smoothness effect to conclude. Okay, how do we conclude? Now we consider like for H delta greater than 0, all right? We can see that because of the above argument, what was the above argument? So the above argument was the fact that epsilon is close. This is a 2 star here. Epsilon is close to uniformly in M. Okay, so what I'm gonna do is that for H delta greater than 0, just for epsilon small enough such that C times epsilon to the power theta is less than delta over 2, we get that U epsilon M minus UM in LQ of V is less than delta over 2 for all M in N. This is important, and for epsilon small. Okay, and now because we also have by the end of the step 2 that U epsilon mk is a Cauchy sequence for fixed epsilon. So we can see that for each of the fixed epsilon, fixed epsilon greater than 0, as U epsilon mk is a Cauchy sequence in LQV, right? We can find a subsequence of this, or you can chop off the first few items. A subsequence of this. Okay, let's still name it by U epsilon mk by abuse of notation, such that we have U epsilon mk minus U epsilon mj LQ V is less than delta over 2 for all k and j in N. Okay, so we have 2 points. The first point is that U epsilon is close to UF. Okay, for once we choose epsilon small enough. And the second point is that for this fixed epsilon small enough, I have this property, right? That U epsilon mk and U epsilon mj is close to each other. All right, so now I can use the triangle inequality to bring things back together, right? So epsilon. Okay, yeah, maybe I need to divide everything by one more epsilon 1 over 2 or something like that. But by combining the two Clem's inequalities above, we yield that just by triangle inequality, UMK minus UMJ in LQ of V is less than equals to UMK epsilon minus UMK LQ plus U epsilon MK minus U epsilon MJ LQ and plus U epsilon MJ minus U MJ in LQ. Okay. So each of this is less than delta over 2. So the whole thing is less than equals to 3 delta over 2. Okay, yeah, it should be 2 delta. Equals to 2 delta. Okay. So what is cool is that you fix a delta. You can run this procedure to have a subsequence so that UMK and UMJ is not far away from each other, right? So now you can, for this, you can select a subsequence and use the diagonal argument, right? Then use this subsequence and choose smaller delta repeatedly, right? Inductively through a usual diagonal argument. Okay. Let's say for delta k, you can choose it to be k is to be delta over 2 to the k to get a subsequence u okay, I'm running out of notation. I'm sorry. Ooh, U L J. Okay. Such that ULJ now, because of the inequality you have, right? So ULJ minus ULK in LQ is going to be less than or equals to delta over 2 to the mean of K and J, right? And this means that this is a Cauchy sequence, and hence, finally, we get from this one is because it's a Cauchy sequence, and then finally we arrived at that. Then it's implied that ULJ is a Cauchy sequence in LQ of V, and thus we have ULJ converge to some U bar in LQ of V. And this helps us to get the conclusion that we get W1P of U is compactly supported. No, not compactly supported. I take it back. It's compactly embedded into LQ of V. U. Okay, so that's the conclusion. I'm sorry, it's in a little bit sort of technical way. But I'll send you the notes. Everything is clear except this sort of very messy inequality. What it tells you is essentially you can always do interpolations. That's all. All right. So that's sort of the very important result about the Rellich-Kondrachov compactness embedding theorem. Let me make some remarks. Okay. The first remark is that in case of W01P of U, we don't need to do extension, right? Because it's W, again, recall that W01P of U by definition is CC infinity of U closure in W1P norm. And hence, if we are given the W01P of U, we don't need to do extension at all. And we can still run the proof of this theorem because we didn't need to extend everything to V, and we didn't have to assume that things have compact support, but we have to be careful, of course, when we do approximations. But if we are careful enough when we run through this argument, then we can get that W01P of U is compactly embedded into LP of U. And this happens even if we don't assume that del U is C1. So even if del U is not C1. Okay, so that's an important result that we have. And the second remark I want to make is that the above proof we only talk about for P less than N, right? So there's we also have this result that for 1 less than equals to P less than equals to infinity, we can still have show that W01, no, not 0, W1P of U is compactly embedded into LP of U. Okay, so this is the claim that I claim. This is true for all 1 less than equals to P less than equals to infinity. All right, let's see quickly how does it happen. Well, you see that so we already proved this claim, right? For 1 less than equals to p less than n. Okay. The same proof should hold for n because you know and actually the same proof should hold for any p greater, because I only need to use the fact that there are different ways to say this, but one simple way to say this is that okay, let's see, for p greater than equals to n, just note that with 1 less than equals to p bar less than n less than equal to p, we do have the fact that w1 p of u is a subset of a bigger set, which is w1 p bar of u, right? Because the bigger the p is, the more integrable we require the function. So w1p is a subset of w1p bar, and w1p bar, we have shown that this is compactly supported in LQ for q less than p star, and in particular this is surely compactly supported in okay in L compactly supported in Ln up here, right? Because as n is less than p bar star, which is n p bar over n minus p bar. Okay. When you choose p bar to be very close to n or whatever, then you do have that n times p bar minus n over p bar can be as close to infinity as you want. And by exactly this point, you can see that for any p less than infinity, you can do this same trick. But what I'm saying here is actually more, is about the fact that this so this shows that this is fine for p equals to n, right? Now for p greater than n, we have already seen by the Mori inequality, we have that w1p of u is a subset of c0 gamma of u for gamma equals to 1 minus n over p, right? And we just proved in class that we have the compactness embedding of c0 gamma of u bar is compactly embedded into c0 of u. Okay. And you can see that this is compactly embedded into c0 of u, and c0 of u is a smaller space than LP of u. And thus we are done, right? Because we have compactly support. This implies that W1P of u is compactly supported into LP of u for n less than p less than equals to infinity, right? Because I've told you sort of things going in a bit sort of complicated way, but it shows that clearly that we can have various sort of further embedding, not just LP, but it can be embedded in other spaces. All right. So that's it for the compactness result. I think that let's see if I can say a bit more. Okay, maybe let me just state what we will do next time, and then we will do it next time. So next time, let me state the Poincare theorem, Poincare inequality, and then we will prove it next time. It's not too hard to prove it, but in the interest of time, I don't have have a lot of time. So Poincare inequality is gonna be well, this is interesting. It will be proved by compactness method. Okay, it's not proved directly, but it will be proved by compactness method, or by proof of by contradiction. But the result itself is extremely important and will be needed and use a lot of time. So let me state it. Poincare equality. It says the following. Let U be subset of Rn be open bounded with C1 boundary. Okay. Let P to be between 1 and infinity. Okay. Then there exists a constant. C depends on the dimensions, the constant P and the domain U, such that I have the LP norm of U minus is average on U, LP of U. Okay. It's controlled by a constant times du in LP of U. Right. So here what it means is that I don't know the boundary of U. If I were to know the boundary condition of U is 0, then we do have the Sobolev inequality, right? But here we don't know the boundary of U. However, it's an analog of the fact that we know the boundary of U by the fact that we are subtracting the average of U on the domain. Okay, so notations. Let me emphasize this. This is a beautiful theorem. And here, of course, we know about the average. The average of U on U is just 1 over the measure of the set U, integral of U x dx, or just the normal average that we have learned all the times. This plays the role as the averaging behavior, because I have to subtract the average in order to compare the LP norm of U minus the average. Is always controlled by the norm of the gradient, right? Remember when we talk about this, we were saying that the Sobolev inequality of we have to check the constant case, right? So when U is a constant, if we don't subtract the average of U, then we wouldn't have the Sobolev inequality. But when U is a constant, then the average of U is just 1, right? Equals to that constant itself. Then in this case, by normalizing the LP norm of U, subtract the average, this is 0, and surely it's also equals to du and LP. This shows that it's a good inequality to prove, because once we subtract out the average, we have a correct quantity to compare. All right, so this is that. We will prove this one in class after Thanksgiving. It shouldn't be too hard. We will move on from here. All right. Happy Thanksgiving. All right, let me stop.